Imagine dropping a digital explorer into like a dense, completely opaque, multidimensional mountain range.
Yeah.
You blindfold it, and you give it one overriding directive, which is to find the absolute lowest valley on Earth.
Right, and with zero map to guide it.
Exactly. And if it fails, the artificial intelligence you're trying to build will, hallucinate or crash or just output total garbage. That is the actual reality of training in AI.
It's a completely wild scenario when you actually picture it.
It is, because we often talk about algorithms as these clean, sterile math equations that just execute logic perfectly. We picture, like, architectural blueprints.
Yeah, highly structured, very predictable.
Right. But an algorithm optimizing a neural network isn't following a blueprint at all. It is on a desperate, blind hike through a really hostile geometry. So we're going into a deep dive today on a fascinating slide deck titled Navigating the Lost Landscape, the Geometric Reality of Machine Learning Optimization.
Which is such a great title, honestly.
It really sets the stage. And we are going to tear apart the mechanics of how this actually works. For anyone listening, if you've ever wanted to crack open the black box of machine learning, this deep dive is going to translate all that complex math into a physical landscape that you can literally visualize.
I think it's a crucial shift in perspective. I mean, when you stop looking at machine learning as just lines of code.
Right, like just an IDE full of Python.
Exactly. When you start visualizing it as a physical entity navigating a geometric space, the reasons behind why models succeed or fail or, take massive computing power to train, they suddenly become incredibly clear.
It's like we are mapping the topography of artificial intelligence.
We really are.
So let's start right at the core distinction the source material makes. We have traditional optimization on one side and machine learning optimization on the other.
Right, the fundamental divide.
Okay, let's unpack this. If I'm looking at standard traditional optimization, I'm picturing a known smooth function like a bathtub.
A bathtub is a perfect way to think about it.
Right, so drop a marble in the tub, gravity pulls it along the smooth porcelain, and it spirals perfectly down into the drain. The drain is the absolute minimum. It's a closed system.
And in that closed system, you possess all the information. I mean, the terrain is static, the function is completely visible to the mathematics.
There are no surprises.
None at all. Your only goal is to find the lowest mathematical point of that specific given shape. You are literally minimizing the exact equation sitting right on your desk.
But the deck immediately pulls the rug out from under that bathtub analogy when it comes to machine learning. Because in ML, we aren't trying to find the drain of the tub you're currently sitting in.
No, not at all.
We are trying to predict the shape of tub we haven't even seen yet, like we're hiking in the fog.
That is the defining separation. I mean, in machine learning, you have a set of training data, right?
The landscape we actually have access to.
Exactly. The landscape you can actively explore and measure. But your objective isn't to find the absolute lowest point of that training data.
Which feels counterintuitive at first.
It does, but your objective is actually generalization. You want the model to perform well on unseen test data, the real world.
Right, out in the wild.
Yeah. The training landscape is merely a proxy. It's a flawed map of the real world.
This brings us to a visual in the deck labeled the projection of overfitting. And I want to linger on this because the mechanics of it are just fascinating.
It's one of the most important concepts to grasp.
So the visualization shows two separate landscapes floating one above the other in three-dimensional space. The top surface is the training data. The bottom surface is the test data, the real world.
Right.
And they have similar broad contours, but the microscopic details are completely different.
And they are different because real-world data contains noise.
Yeah.
I mean, the training set has its own specific quirks, random fluctuations, anomalies that just don't exist anywhere else.
Right, just statistical blips.
Yeah. So if you unleash a highly complex algorithm on the top landscape and tell it to simply find the absolute lowest mathematical coordinate.
Like we did in the bathtub.
Exactly. It is going to hunt down every single microscopic anomaly. It will find this tiny, incredibly deep sinkhole that exists only because of a random grouping of noise in your specific data set.
And the math is going to look at that sinkhole and say, incredible, our error rate is 0.00001. We found the bottom. We did it.
Exactly. The algorithm firmly believes it has succeeded. But then you evaluate that model against the real world.
So geometrically, you take the exact GPS coordinates of that sinkhole on the top landscape, and you project a laser pointer straight down onto the bottom landscape, the unseen test data.
Right, you map the exact same coordinates.
And because that sinkhole was just a localized anomaly, just a statistical ghost,
Uh,
when you project that coordinate down onto the real-world landscape, you don't hit a valley. You hit the side of a massive mountain.
you find yourself at a coordinate with extremely high loss.
It's a disaster.
Total disaster. The model fails catastrophically in production. The algorithm was trapped by the illusion of perfection. I mean, minimizing the training loss too perfectly, driving that error down into those microscopic sinkholes, that is the literal geometric definition of overfitting.
So you completely missed the true general minimum.
Well, you did, and that true minimum is usually a broader, shallower valley that exists in roughly the same place on both landscapes.
Okay, so hitting the mathematical absolute bottom is actually a trap.
A very dangerous trap, yeah.
We are looking for the right valley, the broad general valley, not just any deep hole we can find. But how does our digital explorer actually move to find any of this?
That's the big question.
Because remember, it's blindfolded. It can't see the broad valley or the deep sinkhole from a distance. It just feels the dirt right under its boots.
This takes us to the fundamental engine of movement in machine learning, which is gradient descent.
Okay, let's get into the math, but gently.
I promise it's not too bad. The core update mechanism is defined by a surprisingly compact equation. You take your current weights, which we represent as WG, and you update them.
Right, so taking a step.
Exactly. The new W becomes the old W minus the learning rate, which is alpha, multiplied by the gradient of the loss function, denoted as nabla J.
Okay, I want to break down the physical reality of this equation. W becomes W minus alpha nabla J. Let's establish our parameters here. In a neural network, W isn't just an X and Y coordinate on a map, is it?
No, not at all. W is a vector containing every single parameter, every single weight and bias in the entire model.
Okay, so if we have a modern model with 1 billion parameters, W is a single coordinate in a 1 billion dimensional space.
That is a vital point to grasp, yeah.
Which is terrifying to try and picture.
Right. Our human intuition fails completely beyond 3 dimensions. But mathematically, the geometry holds perfectly. You are standing at a single exact point in a billion-dimensional landscape.
And my altitude at that exact point is my current loss, right? My error rate.
Exactly. And your goal is to lower your altitude.
So we need a direction to step. That's the gradient vector, the nabla E. Now, in calculus, a gradient points in the direction of steepest descent. It tells you the fastest way to climb the mountain.
Which is the opposite of what we want.
Right, because we want to reduce our error, we want to go down. That's why there's a negative sign in the equation.
Exactly. We subtract the gradient.
We point the compass precisely 180 degrees away from the steepest descent. We point it straight downhill.
But the limitation of that gradient is what makes optimization so extraordinarily difficult in practice.
Because it's blindfolded.
Right. The gradient vector is a derivative. By definition, it is an infinitesimal measurement.
It has no map.
It does not possess a map of the mountain, it doesn't know where the global valley is, and it doesn't even know what the terrain looks like 10 feet away.
If it only knows the exact slope of the literal millimeter of dirt I'm standing on, how does that translate into a billion-dimensional step? I'm trying to visualize this.
It's tricky to conceptualize.
1 billion dimensions means we have 1 billion different axes we can move along. How does the gradient vector tell me how to move all of them at once?
Because the gradient vector itself is a billion-dimensional vector. For every single weight in your model, the gradient calculates a partial derivative.
Okay, so it looks at each one individually.
Exactly. It asks a highly specific question for each weight. If I tweak this specific parameter just a tiny, tiny fraction of an amount, while holding the other 999 million parameters perfectly frozen, does my altitude go up or down, and by how much?
Oh, wow. So it calculates that isolated slope for every single dimension simultaneously.
Precisely.
So the gradient vector is really just a massive list of 1 billion individual slope measurements packaged together into one single arrow, pointing down the steepest possible combination of all those slopes.
That's a great way to put it. And once you have that direction, you must decide how far to walk along that line before you stop and recalculate.
Because the landscape curves.
Right. You cannot just walk blindly forever in that one direction. The slope you measured a second ago is no longer the slope you were standing on.
Which introduces alpha into the equation.
Yeah.
The learning rate. My stride length.
Yes. The gradient gives you the direction, but alpha is a scalar value that determines the magnitude of your step. It is arguably the most critical hyperparameter in basic optimization.
Okay, let's push on this stride length problem, because section 3 of the deck dives deep into line search methods. We have our infinitesimal compass reading. The compass says, go exactly this way.
Right.
If my alpha is too tiny, I take a microscopic baby step, recalculate the gradient, take another baby step. I will theoretically eventually reach the bottom, but like the heat death of the universe will happen before my model finishes training.
Absolutely. It's computationally unfeasible. And conversely, if your alpha is too massive, you take a giant bounding leap.
And I jump right over the valley.
You might completely vault over the optimal valley and land on an entirely different mountain peak on the far side, potentially at a higher altitude than where you started.
So the model diverges.
Yes, it diverges. So the algorithm must dynamically or systematically determine the optimal travel distance for every single step.
The deck maps out a decision tree for finding this perfect stride. It starts with a best-case scenario. What if the function is quadratic or unimodal? Meaning, what if the lost landscape is just a perfect, smooth, symmetrical bowl?
Right. If the geometry is a perfect parabola, the mechanics are beautifully simple. You can use an exact analytical line search.
Because it's perfectly predictable.
Exactly. Because you know the mathematical definition of a parabola, you don't need to guess your stride length. You can take the derivative of the function along your specific directional line, set that derivative to 0, and instantly solve for the exact distance to the absolute bottom of that curve.
One calculation, perfect stride length, and you land exactly at the minimum of that specific slice of the landscape.
It's highly efficient.
But we are building deep neural networks. We aren't optimizing a single parabola.
Far from it.
Our landscape is a chaotic, multi-dimensional nightmare. We can't set the derivative to 0 and solve it because the equation of the entire landscape is just way too complex to invert. So exact analytical line searches are out. We have to approximate.
Right. And when you move to approximations, you face a trade-off between computational certainty and computational speed.
Okay, break that down for me.
Well, if you need absolute guaranteed bounds, meaning you must be mathematically certain that the bottom of the valley exists within a specific range before you take a step, you use algorithms like the golden section search.
And I love this part. The mechanics of the golden section search are fascinating. It's basically like a highly optimized game of hot and cold, or like guessing a number between 1 and 100.
It is very similar to that, yeah.
You establish a massive starting interval on your line of travel, point A and point B. You know the minimum is somewhere between them. But instead of just guessing the exact middle and slicing it in half over and over, you use the golden ratio to place 2 test points inside the interval.
And the use of the golden ratio, which is roughly 1.618, is a brilliant mathematical optimization of computing resources.
Why is that specific ratio so important?
Because every time you want to evaluate the altitude of a point, you have to run a forward pass of your entire model.
Oh, right. You have to push all the data through to see what the error is.
Exactly. And if your model is massive, calculating the loss at a specific coordinate is incredibly expensive.
So you don't want to just test random points and throw them away. You want to recycle your tests.
That's the secret. By placing your test points based on the proportions of the golden ratio, when you eliminate a section of the interval and narrow your search window, one of your previous test points is already perfectly positioned in the correct geometric proportion for the new, smaller interval.
That is so smart.
It really is.
Yeah.
You only have to compute 1 new point per iteration rather than 2. The bounds progressively narrow, basically trapping the minimum in a shrinking cage until it is tight enough to satisfy your tolerance, and then you finally take your step.
It's incredibly clever geometry. But even with the golden ratio recycling computations, evaluating the model over and over just to figure out how far to take a single step sounds agonizingly slow for a billion-parameter network.
Oh, it is. It is far too slow for deep learning.
Okay, so what we actually use.
Which brings us to the fast approximation method, the Armijo rule, or the Wolf conditions. In real-world machine learning, we basically abandon the desire to find the perfect bottom of the slope.
We just want to ensure the step is good enough.
Exactly.
But what defines good enough mathematically?
The Armijo rule enforces a condition of sufficient decrease.
A sufficient decrease, okay.
It calculates a tangent line based on your current gradient, and it mathematically mandates that your step must result in a drop in altitude that is proportional to how steep the slope was.
Oh, I see. So if the slope is terrifyingly steep, you must achieve a massive drop in loss to justify the step.
Right. And if it's a gentle slope, a small drop is acceptable. It essentially tests a relatively large stride, and if that stride violates the condition, like if it overshoots or doesn't drop enough, it systematically shrinks the stride, usually cutting it in half, until the condition is met.
So it's a backtracking method.
Exactly.
Try a big step. If it fails the sufficient decrease test, pull it back until it passes. Then commit to this step. It trades the perfect exactness of the golden section search for sheer velocity.
Yeah, we don't need to find the absolute bottom of the local curve. We just need to aggressively force the altitude down and move on to the next gradient calculation.
That is the practical reality of navigating these spaces, isn't it?
Yeah.
You sacrifice precision for momentum.
Always.
And speaking of momentum, let's talk about why we need it. Because we have our compass, we have our fast approximation stride length. We are aggressively stepping down the mountain. But Section 4 of the deck introduces the topography of failure.
The geometric hazards.
Right. It turns out relying purely on the current slope of the dirt under your boots is a fatal flaw when the landscape itself is actively trying to trap you.
It is basic gradient descent, calculating the slope, taking a step, recalculating it, assumes a relatively cooperative geometry.
A nice smooth bowl.
Right. But the loss landscape of a deep neural network is non-convex. It is riddled with geometric traps that exploit the exact mathematical rules the algorithm is following.
Let's physically map these traps, starting with the saddle point.
Yeah.
I really want to visualize the geometry here. Imagine a classic Pringles potato chip.
A very tasty piece of geometry.
Right. If you are standing in the exact dead center of a Pringle and you look forward or backward along the length of the chip, the surface curves upward.
Yes.
But if you look left or right, the surface curves downward over the edges.
The Pringle is a perfect representation of a minimax point in 2 dimensions. Now, apply our gradient update rule we talked about. W becomes W minus alpha nobble J. Remember, the gradient calculates the slope of the dirt exactly under your boots. At the absolute microscopic center of that Pringle, what is the slope?
Well, the upward curve perfectly balances the downward curve. So the mathematical tangent at that specific coordinate is perfectly flat. The slope is 0.
Exactly. The gradient is 0. So the algorithm multiplies the learning rate by 0. The update becomes W minus 0.
It takes a 0-length step.
The algorithm completely ceases movement. It halts.
The compass just spins out. The mass looks at the 0 gradient and says, aha. By definition, a 0 gradient means we have reached the bottom of a valley. We are done.
But you aren't at the bottom.
You are sitting on the middle of a Pringle.
Right. If the algorithm had just blindly taken one single step to the left or the right, it would have found a steep downward slope and continued its journey. But because it relies entirely on the local derivative, it freezes.
This highlights a pretty profound vulnerability in first-order optimization.
It does. The algorithm is blind to the second derivative, the curvature. It doesn't know that the flat spot is actually a ridge and not a valley floor.
And are saddle points actually common?
They become exponentially more common as the dimensionality of your model increases. I mean, in a billion-dimensional space, the probability of finding a true local minimum where every single one of the billion directions curves upward is vanishingly small.
But finding a point where some directions curve up and some curve down.
They are everywhere. Saddle points are the dominant hazard in deep learning.
Okay, so the algorithm stalls on saddles. What about flat regions? The deck mentions plateaus.
A plateau is exactly what it sounds like. It's a region where the gradients simply vanish. The surface is virtually flat in all directions.
Let me guess. The gradient evaluates to something like 0.0000001, so the algorithm takes an infinitesimally small step, evaluates again, gets another microscopic gradient.
And effectively dies of exhaustion before it can cross the plateau to find the slope on the other side.
Just stranded in the desert.
Exactly. Vanishing gradients literally paralyze the learning process. But honestly, the most violent hazard is differential curvature.
Geometrically, this is a steep ravine. Let's build the ravine in our minds for the listener. We have massive, towering cliffs on the left and right, extremely steep vertical drops.
Okay.
But the valley floor between them is very narrow, and it slopes downward very, very gently.
The mathematical term for this is an ill-conditioned landscape.
Ill-conditioned.
Yeah. The condition number is basically a ratio of the steepest curvature to the shallowest curvature. In a ravine, this ratio is massive. The slope down the cliff walls is immense, while the slope along the valley floor is minuscule.
So let's drop our digital explorer onto the side of the steep cliff wall. It calculates the gradient. The gradient screams, the steepest way down is perpendicular to the wall. Jump off the cliff.
Exactly. So the algorithm takes a massive step based on that huge gradient.
But because the valley floor is incredibly narrow, that massive step doesn't just take it to the bottom. It shoots the algorithm completely across the valley floor overshooting the minimum, and it slams into the cliff wall on the opposite side.
It takes a step, and its altitude might actually increase because it landed so high up on the opposing wall.
Then it recalculates. The gradient on the new wall screams, "Jump back!"
Right. It takes another massive step, overshoots again, and slams into the original wall. The trajectory of the algorithm becomes a violent, jagged zigzag, ricocheting back and forth across the ravine walls.
Meanwhile, the actual path to the minimum requires moving gently down the length of the flat valley floor.
Yes, but the gradient along the floor is so small compared to the cliffs that the algorithm barely moves forward. It's burning all its computational energy ping-ponging left and right, making almost zero forward progress.
If I just shrink the learning rate to stop the ping-ponging, what happens? Just make alpha really small.
If you shrink alpha, the algorithm will stop bouncing off the walls. It will safely reach the bottom of the ravine. But because your alpha is now tiny, traversing the long, gentle slope of the valley floor will take millions of iterations. You cure the divergence, but you completely paralyze the convergence.
This is a nightmare. I mean, pure gradient descent is a really fragile mechanism. It freezes on Pringles, it dies on plateaus, and violently ping-pongs in ravines. We need a way to upgrade the physics of our explorer.
Which brings us to Section 5, adapting to the terrain.
Right, and the first major physical upgrade is momentum.
Momentum fundamentally alters the nature of the update rule. Instead of the algorithm acting like a hiker taking discrete, isolated steps, momentum transforms the algorithm into a heavy physical object. Imagine a heavy iron ball rolling down the lost landscape.
Okay, so we are adding inertia.
We're adding a velocity vector. Mathematically, the update rule no longer just looks at the immediate gradient. It calculates an exponentially decaying moving average of all past gradients.
It remembers its history.
Exactly. The new step is a combination of the current slope and the velocity built up from previous steps.
Let's apply this iron ball to our hazards. The ball rolls down a hill and hits a flat plateau where the gradient is 0. A standard algorithm would freeze immediately.
Right, gradient is 0, step is 0.
But the iron ball has history. It has velocity. Even though the local slope is 0, the accumulated momentum pushes the ball forward, allowing it to coast completely across the dead zone until it hits the downward slope on the other side.
It also allows the algorithm to power straight through saddle points, coasting over the flat center before the 0 gradient can halt it.
Oh, that's brilliant.
And if it falls into a shallow local minimum, like a tiny puddle on the side of the mountain, the momentum can carry it up and over the lip of the puddle, escaping the trap.
That is beautiful.
Ah.
Giving the math a memory of where it just was allows it to survive the flatlands. But wait, what happens when our heavy iron ball hits the steep ravine? If it's rolling down the cliff wall, building up massive momentum, and it shoots across the valley,
Yeah.
isn't the momentum just going to make it smash into the opposite wall even harder?
Yes, it absolutely is. Momentum exacerbates the ping-pong effect in differential curvature. A heavy ball bounding down a narrow canyon is chaotic.
Okay, so momentum is great for flats, terrible for ravines.
Exactly. To solve the ravine, we need a different mechanism. We need adaptive scaling. And the deck introduces 2 foundational algorithms for this, Etagrad and RMS-prop.
How does adaptive scaling actually work? How does the algorithm realize it's trapped in a bouncing cycle and stop it?
It requires monitoring a different kind of history. Instead of just tracking the directional velocity, RMS-prop tracks the variance, the squares of the past gradients.
The squares of the gradients.
It maintains a running average of the magnitude of the slopes it has encountered in every single dimension independently.
Okay, let's break down that dimension independence. In our billion-dimensional space, the algorithm tracks exactly how violently the gradient is swinging back and forth on the x-axis, the y-axis, the z-axis, and so on.
Correct. Now let's look at the ping-ponging in the ravine again. Left to right across the canyon walls, the gradients are massive. They are huge numbers, swinging positive to negative.
Right.
RMS-prop sees these massive squared gradients accumulating on that specific axis. Its response is to dynamically shrink the learning rate only for that specific dimension. It mathematically applies the brakes left to right.
It realizes I am burning energy bouncing on the x-axis, so I am going to throttle down my stride length on the x-axis.
Exactly. And simultaneously, it looks at the z-axis, the axis running straight down the flat valley floor. The gradients there are tiny. The squared history is minuscule.
So it does the opposite.
Yes. RMS-prop dynamically increases the learning rate for that specific dimension. It presses the accelerator forward.
Hold on. If we are adapting the learning rate for every single dimension, independently, like shrinking x and stretching z, doesn't that mean we are fundamentally distorting our compass? The combined arrow we take a step along is no longer pointing in the true direction of steepest descent.
That is a brilliant observation. Yes, we are. We are intentionally distorting the true gradient.
Wow.
We are warping the geometry of our steps to counteract the hostile geometry of the ravine. By dampening the steep oscillations and accelerating the shallow progress, RMS prop effectively turns the narrow, steep ravine into a nice symmetrical circular bowl where the algorithm can just walk straight down the middle.
We fight geometry with geometry. I love that.
Yeah.
So momentum solves the flat regions by adding velocity. RMS prop solves the ravines by stretching and squashing the learning rates. So what happens if we crash them together?
You get the undisputed champion of modern deep learning, Adam, adaptive moment estimation. Adam calculates both the first moment, which is the velocity vector of momentum, and the second moment, the squared gradient variance of RMS prop.
It's basically the ultimate all-terrain vehicle.
It is. The first-order diagnostic matrix in the deck outlines this perfectly. Basic gradient descent fails out of both flats and ravines. Momentum survives flats but dies in ravines. RMS prop survives ravines but stalls on flats. Adam utilizes the heavy iron ball to coast over saddle points and plateaus, while simultaneously applying the independent braking and accelerating system to glide smoothly down the center of narrow ravines. It synthesizes the physical upgrades into a single, highly robust update rule.
That feels like a solved problem. We built the perfect rover to navigate the mountains step by step.
It's very effective.
But earlier you mentioned that first-order methods, everything we just talked about, including Adam, are blind to curvature. They only see the first derivative.
Right.
If this step-by-step navigation requires so much hacking and compensating with momentum and scaling, why don't we just use a method that actually sees the curvature of the mountain? Like, is there a way to map the bend of the landscape and just parachute directly to the bottom?
There is. You were talking about moving from first-order optimization to second-order optimization. The primary method discussed in the deck is Newton's method.
Okay, let's get into Newton's method.
First-order methods use the gradient vector, which is a 1D line pointing down. Second-order methods use the Hessian matrix.
Let's unpack the Hessian matrix. What does it actually measure?
In calculus, the second derivative measures the rate of change of the rate of change. It measures acceleration, or geometrically, it measures curvature. Does the slope keep getting steeper, or does it start to level out into a valley?
Okay.
The Hessian is a matrix containing all the second-order partial derivatives for every single parameter in your model.
So instead of just feeling the slope of the dirt under its boots, the algorithm feels how the dirt is bending in every single possible direction.
Exactly. And with that curvature data, Newton's method does something extraordinary. It builds a massive multidimensional quadratic approximation, a perfect mathematical parabola that precisely matches the curvature of the landscape at your current location.
Wait, and because it's a perfect parabola, as we discussed earlier, it doesn't need to guess a step size.
Precisely. It mathematically calculates the exact minimum of that massive parabola, and it leaps directly to those coordinates in a single bound.
It literally looks at the bend of the canyon wall, calculates exactly where the floor should be based on that curve, and teleports there.
Yes.
The visual on the slide for this is almost comical. The gradient descent path is 100 tiny, painful zigzag steps agonizingly working its way down a curve. And the Newton method path is just one giant sweeping arc that lands a bullseye right on the minimum. It solves the problem in one step.
It looks like magic.
Why on earth did we spend 20 minutes talking about Adam and RMS prop when we could just use the Newton method all the time?
Because of the computational cost of curvature, building and utilizing the Hessian matrix encounters a physical limitation of our universe. The deck labels this the cost of curvature, and it uses big O notation to describe the scaling friction.
Yeah, okay, let's look at the numbers. First-order methods like Adam only need the gradient vector. A vector of 1 billion parameters requires 1 billion calculations. In algorithmic complexity, that scales linearly. The computational cost is O of D, where D is the number of dimensions.
And 1 billion operations per step is trivial for modern GPUs. The matrix multiplications are highly parallelized. The friction is incredibly low.
But the Hessian?
The Hessian is a matrix of second derivatives. If you have 1 billion parameters, the Hessian matrix is 1 billion columns by 1 billion rows. It contains 1 quintillion entries.
That is 1 million trillions. Just to store that matrix in memory would require exabytes of RAM.
And storage is the easy part. To actually calculate the optimal jump, Newton's method requires you to invert the Hessian matrix.
Oh.
The algorithmic complexity of matrix inversion scales cubically. It is O of d cubed.
O of d cubed. So for a 100 billion parameter large language model, the computation required for a single step is 100 billion to the power of 3.
That is 10 to the 33rd power operations. For context, the fastest supercomputer in the world right now operates at roughly an exaflop, which is 10 to the 18th operations per second.
So if we commandeered the fastest supercomputer on Earth, how long would it take to calculate one step of Newton's method for a modern LLM?
About 30 million years.
For one step.
For one step. And training a model requires hundreds of thousands of steps.
Okay, that is a hard brick wall. The math is mathematically flawless, but physically impossible to execute. It's a gorgeous theory that instantly vaporizes upon contact with the scale of modern AI.
It really does. And honestly, the computational cost isn't even the only fatal flaw.
There's more.
The deck highlights the risk of divergence. Newton's method fundamentally assumes that the landscape is convex, that it curves like a bowl. It builds a parabola that opens upward. But what if you were standing on a saddle point?
Oh, the saddle point has negative curvature in one direction. It curves downward over the edges of the Pringle.
Yes. If the Hessian detects negative curvature, it builds an inverted parabola, a parabola that opens downward. And when Newton's method attempts to find the minimum of that inverted parabola, it actually calculates the coordinate of the peak.
You're kidding.
Nope. Instead of parachuting you down into a valley, the math violently launches you straight up into the sky. It actively diverges away from the solution.
So second-order optimization is incredibly fragile. It costs the lifespan of the universe to compute, and if it touches a saddle point, it blows up the model. I guess we are sticking with our trusty first-order atom explorer.
Indeed. We trade the elegance of exact curvature for the pragmatic survival of adaptive gradients.
All right, we need to pivot, because everything we have discussed so far, the valleys, the ravines, the plateaus, the saddles, has relied on one massive unspoken assumption.
Which is?
That the landscape is continuous. That it might be steep, it might be flat, but it's fundamentally smooth dirt. You can always calculate a slope.
Yes.
But Section 7 rips that assumption away. We are entering the domain of sharp edges and real-world boundaries. What happens when the terrain is non-smooth?
The primary example the deck uses for non-smooth geometry is L1 regularization. L1 regularization is a technique used to force an AI model to be sparse, meaning it aggressively pushes weights that aren't strictly necessary exactly to zero.
Geometrically, how does L1 change the landscape?
Standard optimization creates U-shaped valleys. The bottom of the U is smooth and curved. The derivative gracefully approaches zero as you hit the bottom. But L1 regularization creates a V-shaped valley.
A literal V. Two straight planes intersecting at a microscopically sharp, jagged point at the absolute bottom.
Yes. And that sharp point, the vertex at zero, breaks calculus. By definition, a function is not differentiable at a sharp corner.
Because there's no single tangent line.
Exactly. If our algorithm is sliding down the left side of the V, the slope is a constant negative value. If it's on the right side, the slope is a constant positive value. But at the exact microscopic coordinate of the vertex, the slope is undefined. It simply doesn't exist.
So if our digital explorer lands exactly on that vertex and tries to run the update equation we talked about, the gradient evaluates to an error. The compass shatters. The code literally crashes.
Exactly. Standard gradient descent cannot survive sharp edges. To navigate this, the mathematics must evolve again. And the first solution is the concept of subgradients.
How does a subgradient stop the crash?
Instead of demanding a single absolute tangent line, a subgradient acknowledges the ambiguity of the corner. It mathematically defines a set of valid slopes.
A set of them.
Right. At the tip of the V, any line that pivots between the angle of the left plane and the angle of the right plane without cutting through the geometry is considered a valid subgradient.
So the algorithm basically looks at this sharp point and says, calculus is broken here, but any direction generally pointing down within this specific cone of angles is a valid guess.
Pretty much. It picks one and takes a step.
It's a mathematical band-aid. It replaces absolute precision with a bounded guess just to keep the program from crashing.
It is a bit of a brute force patch, yes. Which is why the deck introduces a far more elegant mechanism for handling these sharp V values, which are proximal operators. This is where the math gets incredibly clever.
Walk me through the mechanics of a proximal operator, because the description in the deck makes it sound like we are literally tearing the algorithm into two separate processes.
That is exactly what we are doing. We split the objective, Remember, our loss landscape is a combination of the standard smooth prediction error, the U-shape, and the sharp L1 regularization penalty, the V-shape.
Right.
Instead of trying to calculate a gradient for the whole messy combination, the proximal operator technique decouples them.
Okay, so step one. We ignore the sharp edge completely.
Yes. Step one is a standard gradient descent step based solely on the smooth, differentiable part of the landscape. The algorithm takes a step in the direction that lowers the prediction error. It acts like the sharp edge doesn't even exist.
But the sharp edge does exist. If we ignore it, our step is going to land us in the wrong place. We haven't minimized the L1 penalty.
Which brings us to step two, applying the proximal operator. Think of the proximal operator as a secondary, highly specialized mathematical function that evaluates where you just landed and then aggressively snaps your coordinates to a new location that perfectly respects the V-shaped geometry.
How does it know where to snap you?
For L1 regularization, the proximal operator physically manifests as an algorithm called soft thresholding.
Soft thresholding.
Right. It looks at the coordinates of your weights after the first step. If a weight is very close to zero, meaning it's hovering near the sharp vertex of the V, the soft thresholding function simply overwrites that coordinate and snaps it absolutely perfectly to zero.
Wow.
If the weight is far away from zero, it just pulls it slightly closer.
It's like a magnetic gravity. Well, right at the sharp point. If you step too close to the vertex, the math grabs you by the collar and yanks you directly onto the absolute 0 point, instantly achieving the exact sparsity the L1 penalty demanded without ever having to calculate a gradient at the sharp corner.
Precisely. It cleanly separates the smooth, continuous stepping from the discontinuous snapping.
That's amazing. But sharp corners aren't the only non-smooth feature. What happens when the landscape simply ends?
Right. Bounded territories and feasible regions. We are moving from pure abstract math into applied, real-world constraints.
Because in pure mathematics, a parameter can be negative infinity.
Sure.
But if our AI is optimizing the aerodynamics of an airplane wing, the thickness of the metal cannot be a negative number. If it's optimizing a supply chain, you cannot ship -5 delivery trucks.
The physical reality of the problem dictates strict boundaries. The mathematics might indicate that the absolute lowest theoretical valley lies in the realm of negative trucks, but that coordinate is forbidden. We must constrain the search space to a feasible region.
And the most literal way to enforce this is projected gradient descent. The analogy that jumped out at me for this is an invisible electric dog fence.
That is a perfect visualization of the mechanism.
So the algorithm is the dog, running around the yard, which is the feasible region, sniffing the ground looking for the lowest point. It looks across the street outside the boundary, and the gradient says, hey, the slope continues down over there. The absolute minimum's in the neighbor's yard.
So the algorithm takes a mathematical step out of bounds. The vector explicitly calculates a coordinate outside the feasible region.
Right. But the instant those coordinates are calculated, the invisible fence activates. A projection operator mathematically calculates the Euclidean distance between the forbidden coordinate, where the algorithm wants to be, and the absolute closest valid coordinate on the perimeter fence.
And then it forcefully teleports or projects the algorithm directly onto that perimeter line.
The dog runs across the line, and the math violently snaps it back to the edge of the property. The algorithm is forced to slide along the literal edge of the boundary, desperately trying to point outward, but constantly being snapped back to the perimeter by the projection operator.
It is effective, but it sounds incredibly jarring. I mean, you are constantly overwriting the fundamental math of the gradient. You are burning computational cycles calculating a step, and then burning more cycles calculating a projection just to undo the step.
It creates a tremendous amount of computational friction, yes. Snapping variables back to a boundary is mathematically violent. But what if we didn't have to snap the algorithm?
Is there another way?
What if we could fundamentally alter the topography of the landscape itself so that the algorithm naturally, organically wants to stay inside the boundary?
This is section 8, manipulating the terrain.
Right. This is where we stop fighting the algorithm and start playing God with the geometry. The deck details penalty methods and barrier methods. Let's start with penalties.
Okay.
If the projection operator was a dog fence, a penalty method is basically building an enormous artificial mountain range entirely outside our feasible region.
Mathematically, you alter the loss function. You add a massive penalty term that only activates if the constraint is violated. If the variable drops below 0 trucks, the algorithm multiplies that negative value by an astronomical penalty weight and adds it to the overall loss.
So the algorithm takes one step outside the boundary, and instantly its error rate explodes by 1,000,000%. It finds itself standing on the sheer vertical cliff face of this artificial mountain.
And how does gradient descent react to a sheer vertical cliff face?
The gradient points straight down, and the algorithm scrambles in a panic right back down the cliff and back into the allowed region. It's self-correcting.
It is self-correcting, but penalty methods have a severe geometric flaw, which is loose boundary adherence.
The loose boundary adherence.
Yeah. If the algorithm really wants to cross the boundary because the true minimum is very far away, it will continuously take a step out, get penalized, scramble back in, take another step out, and get penalized again. It oscillates violently right at the edge.
Oh, I see.
And if you try to fix the oscillation by making the penalty weight infinitely massive, you ruin the condition number of the landscape. You create such severe differential curvature right at the boundary line that the gradient calculations destabilize and the model diverges.
The cliff is so steep it breaks the compass. Okay, so penalty methods are flawed, which brings us to the brilliance of barrier methods. The deck also calls these interior point methods. If penalties build external walls, barriers build internal resistance.
Instead of waiting for the algorithm to cross the line and punishing it, a barrier method creates a mathematical force field inside the boundary.
Inside the boundary.
Right. The most common is a logarithmic barrier. It adds a term to the loss function that approaches infinity as the algorithm approaches the constraint boundary.
I picture this as opposing magnets. The boundary line is a giant negative magnet, and the algorithm is a negative magnet. If the algorithm is safely in the middle of the region, the magnetic resistance is practically zero. It explores freely.
But as it walks toward the boundary, the resistance curve slopes upward. The closer it gets, the steeper the artificial altitude becomes. It creates an infinite asymptote perfectly aligned with the boundary wall.
The altitude goes to infinity before the algorithm can even touch the line. The gradient will naturally curve the algorithm's path away from the wall.
Exactly. It never crosses the boundary because it geometrically cannot climb the infinite slope to reach it. It stays strictly feasible at all times.
It is a profoundly elegant manipulation of geometry.
Wow.
But the ultimate synthesis of all these constraint ideas, like the mathematical poetry of optimization, is found in Lagrangian duality and the KKT conditions.
Yes. Let's dive deep into this because this concept reframes the entire objective of machine learning.
Right.
When we introduce Lagrangian multipliers, we are no longer just trying to find the bottom of a valley. We are playing a game.
We enter what is mathematically defined as a minimax game.
Exactly. You construct a Lagrangian function that combines your primary objective, minimizing the loss, with your constraints, each multiplied by a specific penalty weight, a Lagrange multiplier denoted by lambda.
So the model is now fighting a war on two fronts. The primary algorithm is desperately trying to push the weights down to minimize the loss. But simultaneously, an adversarial mathematical process is trying to maximize the penalty weights, the lambdas, to punish the algorithm for breaking the rules.
Minimize and maximize.
Minimax.
And the equilibrium of this war, the absolute perfection of this balance, is governed by a KKT condition called complementary slackness. This is the mechanism that proves the constraints are working.
I want to explicitly explain the math behind complementary slackness because the slide illustrates it with a seesaw, and it is brilliant. The equation for this rule is incredibly simple. Lambda multiplied by g of x must strictly equal 0. Lambda times g of x equals 0.
Okay, let's break that down.
Let's define the two sides of that seesaw. G of x is the constraint slackness. That just measures the physical distance between where the algorithm is currently standing and the boundary wall.
Correct. If you are floating safely in the dead center of the feasible region, far away from any walls, your constraint is inactive. You have a large amount of slack. So g of x is a positive number.
Right. And on the other side of the multiplication sign, we have lambda, the penalty weight, the severity of the fine for breaking the rule. Now look at the equation. Lambda times g of x equals 0. If we have a lot of slack, meaning g of x is a positive number like 10, the only mathematical way for that equation to equal 0 is if lambda is exactly strictly 0.
The math literally dictates that if you are safe, the penalty weight must cease to exist.
It turns off.
The adversarial process is forced to turn the fence off. It cannot interfere with your optimization while you are operating safely inside the bounds.
But the instant the algorithm touches the boundary wall, the instant the constraint becomes tight, the slack g of x drops exactly to zero distance to the wall.
And the moment g of x becomes 0, the seesaw violently tips. Because g of x is 0, the equation lambda times 0 equals 0 is satisfied regardless of what lambda is. The mathematical shackles are released. The penalty weight lambda is suddenly free to spike upward to any massive positive number required. It activates with incredible adversarial force to push the algorithm back into the feasible region.
One side of that equation must always be 0. Either the slack is 0 because you hit the wall, or the penalty is 0 because you're safe. They can never both exert influence at the same time.
It is a completely automated, self-regulating mechanism. It balances the desire to find the lowest possible value with the absolute necessity of obeying the laws of physics.
It is the pinnacle of mathematical constraint design. Okay, take a breath. We have dissected an astonishing amount of theory here.
We really have.
We've built a massive toolkit. We have the infinitesimal compass of the gradient. We have the stride length calculations of line search. We have the heavy velocity of momentum to crush plateaus.
We have the adaptive independent suspension of RMS prop to navigate ravines.
We have the O of D cubed computational nightmare of the Newton method's Hessian matrix. We have proximal operators snapping us to sharp edges and Lagrangian seesaws keeping us inside the boundaries.
It's a lot.
It is. So how does an actual human machine learning engineer, someone sitting at a terminal right now, look at a fresh data set and decide which of these incredibly complex geometric tools to deploy?
Well, they don't guess. They follow a highly structured, logical deduction. The final slide in our deck is the machine learning optimizer's decision tree.
I love a good flowchart.
It completely demystifies the dark art of AI engineering. It proves that selecting an optimizer isn't about finding a magic spell. It is a series of calculated compromises based on the known topography of the data and the physical limitations of the hardware.
Let's run a simulation. I want to put this decision tree to the test.
Okay, let's do it.
Let's say I am building a state-of-the-art vision model for a self-driving car. My job is to train a massive convolutional neural network to recognize stop signs in any weather condition. So my data set is massive, tens of millions of high-definition images.
Okay, let's trace the branches of the decision tree. We start at the top. First question. Is the objective function differentiable? Do you have jagged L1 sparsity constraints?
For a standard dense vision network, no. We aren't forcing aggressive sparsity on the pixels. The loss function is generally smooth and differentiable.
We follow the yes, it is differentiable branch. Second question. Are there physical constraints? Do we have bounded feasible regions that the weights absolutely cannot cross?
No. We are just adjusting neural weights to recognize patterns of red pixels and octagons. A weight can technically be any value if it helps reduce the prediction error.
So we follow the no constraints branch. We are in unconstrained optimization. Third question. Is the data set massive?
Tens of millions of high-res images, yes. It's enormous.
The tree hits a hard yes branch here, and it introduces a concept we must expand on: stochasticity.
Stochasticity.
Because your data set is massive, the decision tree explicitly forbids you from using standard, full batch gradient descent.
Why? Because calculating the true gradient, the true compass direction, would require running all 50 million high-def images through the billion parameters of the model, just to calculate the slope for a single step. The computational friction would halt the project immediately.
Exactly. So the tree routes you to stochastic gradient descent, SGD. Instead of calculating the perfect slope of the entire mountain, you grab a tiny random handful of images, a mini batch of maybe 64 or 128 images. You calculate the gradient based strictly on that tiny sample, and you immediately take a step.
But the slope calculated from 64 random images isn't going to be the true slope of the overall mountain. It's going to be a noisy, distorted guess. The compass is going to twitch wildly.
It is extremely noisy. Geometrically, SGD doesn't walk smoothly down the mountain. It stumbles erratically like a drunk hiker.
A drunk hiker, yeah.
But because calculating the step is millions of times faster, the hiker takes thousands of fast, twitchy steps in the time it would take the perfect algorithm to take one. The sheer velocity of the stochastic steps overcomes the inaccuracy of their direction.
Okay, so the tree forces us into the stochastic branch. Next question. Are there ravines, ill-conditioned curvature, or flat regions in the lost landscape.
And here we must analyze the nature of your specific data. You're using high-definition images. What is the geometric implication of an image data set?
Well, images are highly correlated. If you look at a high-res photo, a pixel of blue sky is almost certainly surrounded by dozens of other identical blue sky pixels. The input features are deeply mathematically entangled.
That entanglement in the input data translates directly into severe differential curvature in the loss landscape. High correlation creates massive discrepancies in the eigenvalues of the Hessian matrix.
Yeah.
Geometrically, image data creates some of the most narrow, aggressively steep ravines in all of machine learning. You're guaranteed to experience violent ping-ponging if you just use basic SGD.
So answering yes to ravines routes us to our final destination on the tree. Because we have stochastic noise, and because we're guaranteed to be trapped in severe ravines, the decision tree mandates that we must use an attentive learning rate method. We must deploy ATOM, or RMS-prop.
You followed the geometric logic of the data, and you arrived exactly at the industry standard. Vision models almost universally rely on ATOM or its variants to survive the correlation ravines.
The logic is completely airtight. Let's run one more entirely different scenario to see where the tree takes us. Let's say I am not working for a self-driving car company. I am a researcher in a highly specialized fluid dynamics lab.
Okay, a different world entirely.
I am modeling a highly complex but physically small equation. My model only has 500 parameters. It's tiny, but the accuracy requirement is microscopic. I need absolute mathematical perfection, and because I'm at a national lab, I have exclusive, unlimited access to an exascale supercomputer.
Let's trace the logic again. Differentiable. Yes, fluid dynamics equations are highly smooth. Constraints? No. Massive data set? No. It's a tightly controlled physics simulation.
So we are in the smooth, unconstrained, small data branch.
The final question the tree asks, do you possess extreme computational resources, and is the dimensionality...
Only 500 parameters. This is incredibly small. And I have an exascale supercomputer. The answer is a massive yes.
The tree routes you away from ATOM, away from SGD, and directly to the second-order methods. It instructs you to use the Newton method or its quasi-Newton variants like BFGS.
Because with only 500 parameters, O of d cubed is trivial. 500 cubed is only 125 million operations. My supercomputer can calculate and invert that Hessian matrix in a fraction of a millisecond.
Precisely. You don't need the erratic, stumbling approximations of ATOM. You have the computational luxury to map the exact mathematical curvature of the landscape, build the perfect parabola, and parachute directly to the absolute minimum with microscopic precision in just a handful of steps.
The decision tree is really just a map of resource allocation. Do you have the compute to see the curve? Use Newton. Do you have sharp edges? Use proximal. Do you have a massive, chaotic ravine of pixels? Use ATOM. It entirely removes the black box mystique.
It reveals that AI optimization is basically just applied geometry, governed by the harsh realities of computational cost.
We have covered an unbelievable expanse of theoretical territory today. We started by shattering the illusion of a clean, predictable bathtub drain, and we dropped ourselves into the foggy, multi-dimensional reality of the machine learning loss landscape.
We learned that hitting the absolute bottom is often an overfitting trap, a projection failure against the real world.
We unpacked the infinitesimal blinding nature of the gradient vector and the computational friction of trying to mathematically search for the perfect stride length. We observed the catastrophic failures of raw mathematics when confronted with the physical hazards of saddle points, plateaus, and the violent ping-ponging of differential curvature.
And we watched the algorithms evolve to survive. We added the velocity and momentum to crush the flatlands. We added the adaptive scaling of RMS-prop to dynamically warp the steep ravines.
We stared at the terrifying cubic complexity of the Hessian matrix that makes perfect leaps impossible for modern AI. And finally, we learned how to bend the landscape to our will using proximal operators and the beautiful self-balancing seesaw of Lagrangian duality to enforce the laws of physics on the mathematics.
It is a profound mechanical architecture.
It truly is. So, to you listening, the next time you see a headline about a massive new large language model finishing its training run, or a new AI generating photorealistic video, I want you to strip away the magical thinking. Do not picture a glowing digital brain having an epiphany.
That's not what's happening.
Picture this exact, brutal geometric reality. Picture a mathematical vector, a billion dimensions wide, blindly feeling the slope of the dirt, aggressively adapting its speed, ricocheting off the walls of invisible ravines, and desperately coasting over saddle points, all in a relentless, purely mechanical search for a lower altitude. That is the true engine of artificial intelligence.
It is a striking visualization. But before we conclude, there is one final critical dimension to this landscape that we have intentionally ignored, and it completely shatters the illusion of stability.
Wait, what do you mean?
For this entire discussion, we have assumed that the mountain range is static. We assumed that the hills, the valleys, the ravines, and the barriers were made of solid, unmoving rock. If you stand still, the altitude doesn't change.
Right. The data is the data. The landscape is fixed.
But in the cutting-edge reality of advanced machine learning and systems deployed in the real world, like recommendation engines, high-frequency trading algorithms, or autonomous robotics, data isn't a static pile of rocks.
No.
Data is a continuous, never-ending stream. It flows. The world changes. Human behavior evolves. The economy shifts. The definition of a stop sign might change due to weather or vandalism.
Oh, wow.
The mathematical implication of continuous data streaming is that the lost landscape is not made of solid rock. It is made of liquid. It is a hyperdimensional ocean.
An ocean.
The entire multidimensional mountain range we just spent an hour mapping out is continuously undulating. It is violently shifting, warping, and changing shape in real time every single second, while the algorithm is trying to walk on it.
The ground is literally moving under its boots.
Exactly. The concept drift means that the perfectly optimal deep valley your algorithm spent weeks desperately trying to reach today might literally swell up and violently invert into a towering mountain peak tomorrow.
Which means optimization is never actually finished. You never get to sit at the bottom of the valley and rest.
You never rest. So the profound question that remains at the bleeding edge of AI research is this: how do you build an explorer that doesn't just navigate a mountain, but can dynamically surf an ever-changing geometric ocean? How do you optimize for a world that never, ever stands still?
That is a terrifying and brilliant question to end on. The landscape is alive. I love it. Thank you so much for joining us on this incredible deep dive. Keep questioning the unseen geometry of the world around you, and we will see you next time.